Okay, so let's start today's session. Okay, so I've started sharing my screen, and so this is an NPTEL course on Introduction to Astrophysical Fluids. This is week 11 of the course. My name is Rohan, and I am a TA for this course. So I'm a student at PhD student at ISC Bangalore, and we will start today's session with a brief recap of the previous week, and then we'll go into the content of this week. So, okay. So previous week we actually uh, started actually derived the MHD equations. So prior to that week, we introduced plasmas, and in the previous week, we started uh, the MHD equations, which we derived from the Vlasov equation, which is a counterpart of the Boltzmann equation in case of fluids. So, yeah. So, Vlasov equation is this equation, right? So, where F is the density, particle density distribution uh, in the phase space, and this is the phase space, and it also considers collision of particles, due to which some particles may be scattered in or out of the volume, but the particle density is governed by this equation. Okay. Now, actually, we derived these moment equation from the Vlasov's equation. So I derived this zeroth moment equation, which turns out to be the continuity equation, and which I derived explicitly in the previous lecture. And I posted notes on how to derive the first and the second moment. So the zeroth moment turns out to be the continuity equation. Here, J is the current density, right? So J is basically summation of N E, uh, yeah, NEV, right? So, right, and the first moment equation gives you the momentum equation. So, if you see, the first term is the uh, dv dt, similar to what we had in case of hydrodynamics. Then we also had this del dot p in case of hydrodynamics, and here we have an additional Lorentz force term, right? So this is the Lorentz force. Okay. The second moment gives you the energy equation. So this W is the kinetic energy uh, of the species S. S stands for the species, and QS is the del dot QS is the heat flux, right? So E dot J is the um, is the energy due to the current, and this is the collision term again, right? So we write the complete set of MHD equations like this, where the first four equations are just Maxwell's equation, which we are familiar with. The second equation consists of the continuity equation, so which can be just derived from here. So as I said, J is NEV, right? So, or NEU in this case. And if you multiply n with m, right? So you get the density, right? So that's what is over here, right? Okay. So, right. And we also have the momentum equation, which is this, right? Again, NEU is J cross B, and this is rho du dt minus del P term, and we ignore the collision term for now. So, like as we have studied that, this energy equation is generally decoupled, right? So we don't include that here, and instead we use this Ohm's law, right, which is J equals to sigma E plus E plus V, and it is supported by the equation of state. So this forms a complete set of MHD equations where uh, you can see that there are like 8 equations and 8 variables. Okay. Well, there are actually more than 8 equations because these are vector equations. So yeah. Uh, okay. So next, we also derive the generalized Ohm's law, right, which is written over here. But in general, we only take the left-hand side and we neglect the right-hand side of this generalized Ohm's law. But we actually derived the uh, generalized Ohm's law in our previous lecture. Now, well, we also derived the induction equation from the Maxwell's equation. And this induction equation is important in the sense that it talks about how the magnetic field evolves with time, right? And so this is the del cross E cross B, and this is the eta, which is the resistivity, times del square B. So this term talks about diffusion of the magnetic field, and and this is how the magnetic field is advected, right? So this is the advection term, this is the diffusion term. And if you remember, when discussing hydrodynamics, we talked about the Reynolds number, which is basically the advection term V dot del V divided uh, by the diffusion term, which is nu del square V. So, right, and similarly, we have this. We can define a magnetic Reynolds number in a similar way by taking the ratio of this del cross E cross B with the diffusion term, and this magnetic Reynolds number turns out to be uh, proportional to this. So yeah, so basically uh, for high magnetic Reynolds number case, when Reynolds number is very high, uh, we can actually neglect the first term, and then the system will be diffusive in nature. Well, sorry, actually, mu naught sigma is, so if Reynolds number is high, so mu naught sigma is high, right? So mu naught sigma being high, this term will be neglected, and we only be left with this term. So this is a non-diffusive system, right? And which we call as the ideal MHD uh, regime, right? On the other hand, if Rm, the magnetic Reynolds number, is very less, in that case, the resistive term dominates, and the induction equation becomes highly resistive and is dominated by the second term. Okay. So similarly, we also saw, or actually I posted the notes of how you can derive the energy equation in the conservative form, right, from this second moment, right? And this is how it turns out to be. So the change in total energy, and the total energy consists of the kinetic energy plus the internal energy plus the magnetic energy, and it is dependent on the flux of the respective energies. Right. Well, after that, we kind of uh, you know um, transform this momentum equation, right, into we just did a change of variables uh, where we represented the V plus V and B. We replace the V velocity and the magnetic field in terms of Z plus and Z minus, and we derived this equation from the momentum equation, and we see that that the equation gets reduced down to the form to this form in terms of Z plus and Z minus. So this is a similar equation like z plus, the change in z plus with respect to time is affected by uh, z minus, and then we have the del p term and the diffusion term as well. So z plus, so why we are doing this, why this transformation of variables is useful, is because this has a physical meaning, and which means that z plus represents waves propagating along the magnetic field, and z minus represents waves propagating against the magnetic field. And from this equation, we can see that z plus is affected by z minus, and z minus is affected by z plus. So the nonlinear terms separate cleanly, and cross helicity conservation becomes transparent, which also we derived in the last lecture. And energy transfer between the modes are very apparent. And we also saw that the energy of the system depends on z plus square plus z minus square. Okay. So this is up to what we have discussed in the previous week. So let me know if you have any questions, or we will move into the topic of this week. Okay, so so this week we will basically talk about magnetohydrodynamic waves, and then we will see, we'll do a bit of analysis on those waves. What are the types of waves and uh, how they are formed and so on. And after that, we'll talk a little bit about turbulence and a few prescription of turbulence. And yeah, that's it. And then we will uh, go into detail of turbulence in the next week. Okay, so right. So while doing hydrodynamics, we studied sound waves, right? So which are transverse waves that travel uh, inside the uh, inside the hydrodynamic fluid, right? So similarly, we want to do the analysis of well, sound waves were longitudinal waves, right? Anyway, so similarly, we want to do the analysis of uh, of the waves that are generated in case of magnetohydrodynamics, right? So right. So the way we are gonna derive this, uh, do the analysis for for deriving the waves and their dispersion relation is by using the perturbation theory, which we have used earlier as well. So what we're going to do is we are going to take the magnetohydrodynamic fluid uh, or plasma in their base state, right? So in the base state, the plasma has some density rho m naught, right? So this subscript naught denotes the quantities in the base state, right? Similarly, B is B naught in the base state, P is P naught in the base state, right? And then what we do, and velocity is obviously zero in the base state. So then what we do is we introduce perturbations, linear order perturbations, to the base state plasma, and then we are gonna use the equations of microdynamics, like the continuity equation, the momentum equation, the induction equation, uh, and the equation of state. And using those equations, we are gonna derive the dispersion relation. So yes, so as I said, the perturbations are being represented by subscript 1, right? And the base state is represented by subscript 0. So this is the velocity, density, magnetic field, and pressure after we have applied the perturbations. Right? And then we are gonna uh, you know use the continuity equation and put the uh, perturbations, put the values of rho and u, right? And we are gonna evaluate the equation up to linear order, and this is how these corresponding equation turns out to be. So this is how the continuity equation turns out. This is the momentum equation. This is the induction equation. This is the uh, equation of state, right? So, well, yeah, and we do take a polytropic equation of state. So after that, well, let me go to my notebook and then try to derive the. Uh, so we want to go from this to this, right? From this equation to this equation, and we will see how to go from here to here. Right? So let's go to the notebook. Okay, so okay, let me just write down the equations first. Okay, so these are the equations, and what we are going to do is we're going to do a uh, Fourier mode analysis of the equations. And so, what do I mean by Fourier mode analysis? Or basically, what we are going to do is just take Fourier transform of all the equations. And it turns out that so rho m1 we can represent rho m1 as rho m1 tilde, where tilde is the Fourier transform of rho m1, right? Okay, and yes, so rho m1 is the Fourier transform. Rho m1 tilde is the Fourier transform of rho m1, and as we know that when we take Fourier transform, the del t reduce gets well gets transformed to minus I omega, and the divergence operator gets transformed to ik, right? Or you can think of these as a wave uh, of the form e to the power of ikx minus omega t, and if you take del t, you will get this, and if you take the spatial derivatives, you get this. Okay, so yeah, now we're going to see what each of the equation becomes. So so the first equation, the continuity equation, becomes like this. Okay, so I'm just dropping the subscript of 1 because, yeah, because we just have tilde for this. So basically this is equivalent. So I'm just not using the one subscript. So this is the first equation, and this is the second continuity equation. Sorry, this is the momentum equation. Okay, and how about the induction equation? Right. So these are the three equations, and also we can write down the equation of state, right? So where Vs square is the sound speed, right? Gamma p by rho, and this can also be written as Vs square rho m naught by omega k dot u. So this is from here, right? So I just replace rho m tilde with rho m naught k dot u tilde divided by omega, right? So yeah, so this is from here. Okay, so okay, we have four equations now. So now let me okay. So what we are going to use is mainly this equation, right? The momentum equation. Okay, and let's do one thing. So from this momentum equation, what we want to do is, so we you see we have u tilde, b tilde, and p tilde. So we want this whole equation to be in terms of u tilde only, and we can replace b tilde using this equation, and we can replace p tilde using this equation. Okay, so yeah, so just replacing that, what we get is omega square u tilde equals to minus omega by mu naught rho m naught. Well, rho m naught, b naught, so these are okay, right? Because these are just uh, constants, right? Because these are of the base state. So this should be vector mu naught rho m naught k cross b tilde times p naught plus vs square k dot u tilde. Okay, so just replacing p with this, right, and b with this. So let's replace b with this, and this becomes this thing. Okay, times p naught plus vs square k dot u tilde, right? Okay, so this is the equation that we have, right? Now, without any loss of generality, we can take, well, we need, so we can take b naught. So this equation is dependent on b naught and k, which are two constants, right? And another thing that we can do is what we have earlier done as well is we can take B naught by mu naught rho m naught as the Alfvén speed, right? So anyway, so we don't need to worry about mu naught rho m naught, but let's define B naught without any loss of generality as to be only in the z direction, okay? And we can take k to be like this, right? So I think I just have a figure over here. So this is how the direction would look like. So B naught is, we just take Z direction to be the direction of B naught. And then the angle between the uh, propagation of the wave, which is K, and the B naught is theta, right? And this plane, we can define a plane using two vectors, and this plane is the XZ plane, okay? So we can do that. So this is cos theta. Okay. Now, now, okay. Now we just use this relation into this and simplify this equation, right? So this will turn out to be omega square, and we divide by k. So omega square by k, ux tilde, uy tilde, uz tilde. Just writing it in matrix form. This is u. It has three components, which is equals to Vs square. So Vs square, because as I said, B naught by root over of mu rho is the Alfvén speed, and you have two factors of B naught. So this will be Vs square. Okay? And if you solve this cross product, right? So this will come out to be ux tilde uy tilde cos square theta 0, right? And so this is this term plus the last term. So this is k times k dot u, right? And again, if you solve this, this will turn out to be something like this: 0 ux tilde sine theta cos theta plus uz tilde cos square theta. Okay. So then what you do is you just take all of them together, which means that so you have this ux, uy, and uz, right? And you have some coefficient multiplying with it. And if you rearrange this equation, you will just come out to be this equation. Okay. So where Vp is the phase velocity given as omega by k. Okay. So yeah, so if you just rearrange this equation, you will just come out to this equation. Okay, so for example, if you see, this is, well, this should be k square, I guess. Yeah, this should be k square. So for example, the coefficient of ux is omega square by k square minus va square minus vs square sine square theta, right? So this is what you have over here: omega square by k square minus v square sine square theta minus v square. Okay. So similarly, you can see the other factors as well. Okay, now, so this is an equation of the form of ax equals to 0, right? So this equation only has solution when the determinant of this a is equals to 0. So we just take the determinant, and the determinant turns out to be this equals to 0. And from there, if you see, we have an equation whose which can be factored like this. And so we have either this term is 0 or this term is 0, right? And and this is actually uh, a third order equation in Vp square. And so you have three roots of Vp square. Okay. So the first root comes from this term, right, which is this solution, right? And the other two roots comes from uh, this term, right, which is this one and this one. So if you see, this is Vp, as I said, is the phase velocity omega by k, and this one is called the Alfvén wave, and this one are called the fast and slow magnetosonic waves, depending on whose magnitude is greater. Okay. So here is the plot of the Vp, the phase velocity with respect to theta. So if you see that, all these three waves, the phase velocity of all these three waves depends on theta, the Alfvén speed of obviously, which is, as I said, b divided by root over of mu rho, the sound speed, right, and theta, as I said. Okay. Whereas the phase velocity of the Alfvén wave do not depend on the sound speed. And if you plot these solutions with respect to theta, this is this is the case for VA greater than VS, right? So VA depends on magnetic field, right, and VS depend on gas pressure. Okay, so if you have a very strong magnetic field in the system, VA would be greater than VS, right? On the other hand, if you have weak magnetic fields, VA will be less than VS. So in case of strong magnetic field, VA greater than VS, uh, if you, this will be as is, but let's look at this first solution, right? If you take VA much greater than VS, so we can well we can neglect the VS from here, right? And this at theta equals to 0, right? At theta equals to 0, if you see sine, this term will vanish, and we will have this VA square minus VS square. So VA will again vanish, and this will be only VS square, right? So this slow magnetic wave, slow magnetosonic wave. So this solution will then give the slow magnetosonic wave solution. Whereas this solution at theta equals to 0, this term vanishes. So VA square, well, just give me a minute. I think these two are, I've written the same solution. Okay, so this will be plus for one of the solutions. Okay, yeah, I will verify this once. Okay, yeah, so actually it should be plus. Okay, so one solution would be minus and another solution will be plus. So in case of in this case, this will be the slow magnetosonic wave solution, and this being plus, this will be the fast magnetosonic wave solution, because this will be if you this term vanishes at theta equals to 0, and this will be the VS square and the VS square cancels, so this will be VS square, right? And at theta equals to 0, you have VA. The solution will be VA, and similarly, the Alfvén wave also will have magnitude VA at theta equals to 0. And since VA is greater than VS, so this will be the fast solution. The plus solution will give the fast magnetosonic solution, whereas it will be reversed in case of Va less than Vs, where uh, this one will be Va, and this one will give you the slow magnetosonic solution, and and the Alfvén wave will still be Va at theta equals to 0, and the wave will have same velocity as the slow magnetosonic wave velocity at theta equals to 0, right? And this one will give the fast magnetosonic wave solution. Okay, so I hope that's clear. So there is just a typo over here. So this one will be plus, one solution is minus, one solution is plus, which we can get directly from here. Right. So these are the three waves that are getting generated for magnetohydrodynamic waves. Right. Okay. So we'll just go a little bit detail uh, into the analysis of the solutions that we just saw. So okay, so now we want to study, uh, you know, in which directions are the waves propagating, and in which directions are the magnetic field and the electric field, with corresponding to each of the solutions. Right? So, well, so let's talk about the Alfvén waves first. Okay. So, right. So this is the solution of the Alfvén waves, right? Vp square equals to Va square cos square theta. Now this is basically an eigenvector equation. This is a matrix equation, and this can be reduced to a something like that. So when Vp square is Va square cos square theta, you see this term vanishes, right? Whereas the rest of the terms survives. So when this term vanishes, uh, what you can have is you can have any value of uy, right? Whereas ux and uz has to be 0 in order to satisfy this equation. Okay, because ux and uz will be multiplied by these terms, right? Whereas uy will will be multiplied by 0, right? So from here we can directly say that, okay, so Alfvén waves has this um, uy non-zero, has their velocity in the y direction only, and ux and uz has to be 0. Okay. Okay. Now, okay, we got the velocity right. Now, what about the magnetic field, right? So that actually comes from this equation, right? So if you remember, when we take the Fourier transform of this equation, this term becomes I omega b tilde, right? And we have del, this becomes ik, so k cross uh, u tilde cross b naught. Okay, so well, b naught and uh, sorry, b naught and k, we already know the directions, right? So this is the b naught direction, which is z. K is at an angle theta to it, right? And u is, as I said, is in the y direction, right? Uh, and b, from that equation, if you solve, so you can get that b also is only in the y direction. The rest of the component of b doesn't survive. So let me just show maybe from the notebook here. Let's just see from this equation. So b tilde is actually k cross u tilde cross v naught. Right? So u tilde, as I said, is in the y direction, B naught is in the Z direction, and K is in the XZ plane. Okay. So K is in the XZ plane. So if you see, so Y cross Z is minus X. So that is minus Y cross Z is minus X, right? And if we take the X component of K, you can see that uh, this X cross X will vanish, right? So only the Z component of K will give rise to a non-zero B tilde. So if we take Z cross, so Z cross X or Z cross minus X will give you Y, right? So only the Y component survives. Okay. Right. So yes. And if you try to get the magnitude of this magnetic field, so this is how it will turn out to be. Okay. Right. So, and as you see, so there is a minus sign over here. So U and B will be in opposite directions of Y. And similarly, because these plasmas are, uh, you know, ideal plasma, so we can also get the value of E from the ideal MHD condition, which is E plus U cross B is 0, right? So, so from there, you can also get the value of E, okay? Right. Or I guess you can also get the value of E from the Maxwell's equation, maybe. So del cross B is del E del T, right? And then if you take the Fourier transform of that, uh, yeah, or I think this is done from the ideal MHT condition only, because E is minus U cross B, and you have this in Y direction, B naught is in the Z direction, right? So the Y cross Z will give you an X direction electric field, right? And the magnitude is just UY B naught, right? Actually minus, because E plus U plus B is 0. So yeah. Okay. So this is how you get the U from the matrix equation. Similarly, you got the B uh, from the induction equation. You got the E from the ideal MHD condition, and finally you can also get the rho uh, from again um, from the from the continuity equation, right? So if you remember the continuity equation, let me just show it again, maybe. So this is the continuity equation, right? So if you want to obtain rho m, you have to evaluate k dot u, and if you remember, k is in the so k over here is in the x and z direction, whereas u is in the y direction, right? So k dot u will become 0. So therefore rho m is 0, right? So yeah, so I guess you can obtain rho m like that. So rho m 0, what does it mean is that uh, uh, so rho m is the perturbation, right? So rho m1 actually it is, which is the perturbation. So it means that the fluid is uh, cannot be perturbed, or the rho density, the base density of the fluid is uniform everywhere. Rho m naught is constant everywhere. and it just means that the fluid is incompressible, right? So that is the basic definition of incompressible fluids. So, so we have written here, since there is no compression, the fluid pressure and temperature play no role in propagation of this mode, right? So other things I think you might have noticed. So these are transverse waves, right? And and well, transverse because uh, k dot u is zero, right? And also, if you see the Poynting flux, which is E cross B, it's X cross Y, which will be in the Z direction, which is uh, perpendicular to the yeah, velocity, and the direction in which the fluid is moving. Right. So yeah, so that is what I've written. The Poynting flux is parallel to the static magnetic field, which is uh, in the z direction. The electromagnetic energy flow is then exactly along the static magnetic field, independent of the wave angle. Okay. So another thing that people like to visualize these Alfvén waves is by using a taut string analogy, which states that, so if you have this magnetic fields along this direction, whereas the wave is moving uh, at a slightly different angle from the magnetic field, the k direction, and the waves are moving the energy. Although the wave is moving, you know, along a direction from the magnetic field, the energy flow is actually along the uh, along the direction of magnetic field. Kind of how, you know, uh, a taut string, in a taut string, if you just perturb the string, the wave flows along the string, which in this case is the direction of magnetic field, but the motion of the wave is slightly, at a different angle. Okay, so these are not, so the particle motion is not along the magnetic field. Okay, right. So now coming to fast and the magnetosonic waves. So what are the directions of magnetic electric fields, and whether they are longitudinal or transverse and so on. So let's have a look at that. So okay, so this equation uh, is what we get from this equation. Okay, so what we do is that first I mean, the complete general analysis of the fast and slow magnetic sonic waves will be difficult. So what we do is that we just do this analysis at different angles. So let's first take theta to be 0, and then we'll do the analysis for theta equals to pi by 2. So this equation, again, starting from this equation, um, and taking theta to be 0, and we can just remove uh, this row, because this row will give you the Alfvén wave solution. So we just take the first and the third row and we rewrite this equation, and this is how it turns out to be for theta equals to 0, right? So we just remove the second row, right? So now from here you can see, uh, well, uh, so this is one of the solution. So one of the solution is with non-zero ux, and another solution is with non-zero uz, right? So so this is basically an eigenvector equation, right? So here the only two solutions could be, the eigenvectors could be 1 0 and 0 1. Okay, and corresponding to the cases when Vp square equals to Vs square and Vp square equals to Vs square. So when Vp square equals to Va square, the Alfvén speed square, then this term will become 0, right? And then we'll have this first solution. right? And whereas when Vp square equals to Vs square, this term will become 0, and then we'll have the second solution. Right? So I hope that's clear, right? And these two represent the fast and the slow magnetosonic waves, depending on whether Va is greater than Vs or Vs is greater than Va, like we discussed earlier. Okay, and similar, like doing a similar analysis like we did for the Alfvén waves, we can get the magnitude or the direction of the magnetic field and the electric field and the density. Okay. Similarly, we can do the same for this solution. So one thing to notice is that for theta equals to 0, this is a completely an electromagnetic wave solution because this has no compression, again, similar to Alfvén waves. So this is an electromagnetic wave solution. Okay. Whereas for this other solution, you see the electromagnetic field is completely 0. The E is 0, the B is 0, right? So, so this is actually coming from the fact that the U is in the Z direction and the B naught is also in the Z direction. So U cross B is 0. So B is 0, similarly U is 0. And but this rho M is not 0 actually because, uh, because K dot U will give you something non-zero. So this is here the electromagnetic field is 0. So there is no electromagnetic wave, but we do have a compressional wave. Okay. Similarly, for theta equals to pi by 2, that equation reduces down to this. And here we have only one solution where the solution is Vp square equals to Vs square plus Vs square. Okay. So this is the only one solution. This Vp square cannot be 0, right? Because Vp is omega by k. So yeah, that cannot be 0. So the only one solution is Vp square equals to Vs square plus Vs square. And in that case, this becomes 0. So you can see that this the only x component can be non-zero. The z component has to be 0. So the velocity u will be like this. And similarly, we can calculate b and e. And we have this density as well. Okay. So right. So this solution has both electromagnetic and compressional components, right? So that's what I've written. So both transverse and compression longitudinal components are present for fast and slow magnetic sonic waves, unlike Alfvén waves, which has only transverse waves. So we did the analysis for 0 and pi by 2, but for all intermediate angles, both the magnetosonic waves, the slow and the fast magnetosonic waves, have both longitudinal and transverse components, right? Okay. So yeah, so this is how the image would look like. Okay. Right. So so this is the one, the first solution. Okay. This solution. B naught is in the Z direction, B tilde and U tilde are opposite, and E has only component the Y direction. Okay. And this is the K. Okay. And for the slow magnetosonic waves, this is how it looks like. U tilde is along B naught, which is along Z, and K is at an angle theta. Okay, so right. Okay, so those are all about Alfvén waves and fast and slow magnetosonic waves. Now we are going to move to look at some of the instabilities and how they are generated in this MHD systems. Okay. So we have done a lot of instabilities in case of hydrodynamic systems. So here we are going to study about some of the MHD instabilities. Right? Okay. So okay. So before going into instabilities, I just want to introduce one concept which is called the force-free uh, concept. Okay, so what we mean by force free? So if you see, let's have a look at, okay, so this momentum equation, right? So here we are going to consider steady state. So steady state uh, means that the del t ddt would be zero. Right? So we are left with only j cross b equals to del p. Right? Now, if the pressure of the system is very low, or in other words, the system is dominated by magnetic field or has very strong magnetic fields, then we can neglect the pressure force on this equation, right? Because it's very low. So del P goes to zero. So the equation reduces down to J cross P equals to zero, right? So that is basically what force free means, right? So it means strongly magnetized system and J cross P would go down to zero. Right? Oh. So we're just going to see what are the consequences of this force free condition. So from the Maxwell's equation, we can write mu naught J is del cross P, right? And and this has to be, uh, you know, proportional to B, because this is J, and if J cross B is zero, this vector has to be in the same direction as B, right? So this is some scalar function, which could be a function of space, but uh, the main idea is that J has to be in the same direction as B. Okay. Right. So we have this equation, and from there we take divergence on both sides. Right? So we take del dot del cross P, and this divergence on this we use the chain rule, and we have alpha del dot B plus B dot del alpha. And as we know that del dot B is zero from no monopole constant, so this reduces down to the fact that B dot del alpha is equals to zero, right? Because this is zero, divergence of a curve is zero. So B dot del alpha is zero. So now what does it mean is that uh, you know uh, if we have some surface which has constant alpha, so B will be, the magnetic field will be along that surface. So this is exactly what it means. If we have constant alpha surface, where alpha is, as I said, is any scalar function, and which is determined by this relation between J and D. Okay. So along that uh, surface, B will be, yeah, so basically the magnetic field will be along that surface. So if we just want to look at an example, okay, so here uh, we consider this magnetic field configuration, B phi and BZ, like this. And okay, so this just states that, we have an magnetic field along the z-axis, which, so rho is actually not the density, rho is the uh, radius and cylindrical coordinates, right? Okay, so yeah, let's not confuse that with density. So this gives you a magnetic field as a function of distance from the axis, right? So as you see that, as you go further and further from the axis, the z component actually decreases, and but on the other hand, the phi component, uh, well, decreases much slowly, right? Uh, in fact, the b phi at a larger radius will have, b phi will be larger at some radius. Okay. Anyways, so from here we can actually calculate the j, sorry, from this Maxwell's equation, del cross B equals to mu naught J. So if you have a magnetic field of this configuration, we can calculate J, and the Jz will turn out to be something like this. Okay? Right. Now we can, from this, just from the configuration of the magnetic field, we can actually see the surface, calculate the surface along which the magnetic field will lie. So which is given as alpha from this equation, mu naught J by B, right? So alpha is mu naught Jz by Bz, which turns out to be 2k by 1 plus k square rho square. Okay, and which is drawn over here, and it shows that, so this magnetic field are along these surfaces of constant alpha. So these are surfaces of constant alphas, right? And another thing that, and the lines, these are the magnetic field lines which lies on this surface of constant alpha. Another thing to notice here is that, if you have uh, surfaces at smaller radius, right? So this surface, right, which is at a smaller radius, the BZ component actually dominates, right? Because BZ would be greater than B phi. Whereas if you go to larger and larger radius, so these surfaces, the B phi component will dominate, right? And you see that, this magnetic field lines are almost in the phi direction, whereas in the uh, smaller radius surface, the magnetic fields were in the z direction almost. So this is the z direction, by the way. So the horizontal direction is the z direction. Okay? Right. So yeah. So in astrophysics, so these systems are, observed in case of solar coronas, like we studied, right? At the sun's surface, we have these sunspots, right? So the sunspots are regions of very high magnetic field activity. Right? So you have this magnetic fields which are, coiled around somewhat like this shown in the figure, and they rise from one sunspot to another, right? So this, if you see in this figure, so these form this, this magnetic field lines are, coiled around this constant alpha surfaces, which are starting from one sunspot to another, and similar to what has been shown in this diagram or this diagram. So if you just, you know coil this uh, tube, right, you will get a similar structure like this, right? So that was the uh, concept about force free, and this is the consequences as we saw. Now we are gonna study about what if the uh, system isn't force free. So that's called the forced balanced equilibrium. And at equilibrium, as we know, since there is no, we're considering steady state, there is no time derivative. So the pressure will not be negligible anymore because this is not force free, as I said. So the whole equation, the momentum equation, as we saw, was J cross B plus del P, right? So this will reduce down to this equation, right? So, well, actually, it will not reduce down to this equation at the first step, but as we saw in the previous lecture, so we can uh, write this term J cross B, right? We can write this J cross B as del of B square by 2 mu, which is the magnetic pressure, plus 1 by mu naught B del dot B, which is the magnetic tension, right? So we actually derived that from J cross B, right? So it can be broken up into two parts, del B square by 2 mu and 1 by mu naught B del cross B. So that del B square by 2 mu part can be clubbed with del P, and that will give you del of P plus B square by 2 mu equals to 1 by mu naught B del dot B, right? Okay. So now if you reduce that equation, and take cylindrical coordinates, this equation will be reduced down to this part. So this right hand side is basically the magnetic tension part, B del dot B term, and inside you have the pressure. So you have only magnetic fields in the phi and z direction. Okay? So this is the equation it will reduce down to, and similarly you can uh, you know obtain the currents from the Maxwell's equation, like we said, using mu naught j equals to del cross B. And as I said, B has only components in the z and phi direction, right? Such that the del cross B equals to 0 condition holds, and this is how the current will be, right? Just from the Maxwell's equation. Okay? Right. So this is in cylindrical coordinates, right? Okay. Now we are going to study about pinch instability from just these two equations. So what does pinch instability mean? Is that, so let's say, so this is the general equation, right? Now we're going to study about Z pinch and phi pinch. So what does it mean is that when you have, so in case of Z pinch, what you have is that the magnetic field, the Z direction of magnetic field will be zero. Okay, so this term will become zero. So this whole equation will reduce down to this equation, right? So since BZ is zero, and if BZ is zero, okay, so J phi, if you see, J phi will become zero. So the current has no phi component. So the current is completely in the Z direction, right? And so this is how the configuration of the system will look like. B is completely in the phi direction. Z is completely in the Z direction. Sorry, J is completely in the Z direction. So you have uh, this current, which is held by this magnetic field lines, similar to what has been shown in this figure, right? And this is what is called the Z pinch. Okay, and well, if you perturb the system, this will lead to what we call as the pinch instability. Okay, so right. So let me actually give an example of pinch instability, which will make it more clear. Maybe. So let's go to the notepad. So in case of pinch instability, as I said, you have the current only in the Z direction. So let's say you have this kind of a configuration where the the for radius less than a only, the current exists. Outside that radius, there is no current, right? What we were seeing in the figure, where you had this Z and like this, and the magnetic field lines like this. So these were B phi, this was GZ, JZ. Okay. So from here, the magnetic field will turn out to be like this, just coming from the Maxwell's equation. Okay. Okay. So now the current we know is Jz times area. Area is 2 pi rho d rho, which is pi a square j z naught. J is current density, right? So current times, so current density times area is current. Okay, now let's look at the equation, the main equation which we had for the force balanced equilibrium. So this was the equation. From here we know both b phi, right, and we just we can calculate p, right. So how do we do that? Is dp by d rho equals to minus b phi squared by mu naught rho minus 1 by mu naught b phi db phi by d rho, right? And from here we have b phi, and if we do db phi by d rho, it will be mu naught I by 2 pi a square, right? And if we just substitute db phi by d rho from here, what we will get is dp by d rho is equals to minus 1 by mu naught rho, mu naught I rho by 2 pi a square. So this is b phi square minus 1 by mu naught b phi times db phi by d rho. So this is only for the um, rho less than equals to a. Okay. And right. So if you just solve this, so let's see. So 1 mu naught cancels with 1 mu naught in the first term. Rho 1 rho cancels. So mu naught I square rho by 4 pi square a to the power of 4 minus, okay, here 1 mu naught cancels with here. So here again you have mu naught I square rho by 4 pi square a to the 4, right? So this will be minus mu naught I square rho divided by 2 pi square a to the 4. Now we just integrate dp from rho to a, right? Rho is any radius within a. So rho to a mu naught I square rho prime 2 pi square a to the 4 d rho prime, right? So this will be rho prime d prime. Rest are all constant. So rho prime d prime means rho square by 2. So from here we can write pa minus p rho is equals to minus mu naught I square by 4 pi square a to the power of 4. So this, the 2, the rho square by 2 comes over here, and we have rho square from a to rho, which is given by a square minus rho square. Okay. So PA turns out to be 0 because the pressure vanishes at the boundary. Okay. So the P rho will finally become mu naught I by 2 pi a whole square times 1 minus rho square by a square. Okay. So this is what it reduces down to. Okay, so all right, so this is how the pressure varies as a function of rho inside this column. Okay, so what else you can do is, uh, yeah. So I think this is how you can get the pressure, right? Just from the magnetic fields. Okay, right. So now coming back to another configuration, which is the phi pinch, which is just the inverse of the z pinch, where uh, we have the current in the phi direction, whereas the magnetic fields are in the z direction. So if you from this equation, if you do b phi is 0, you'll get this equation, right? And which just says that uh, this p plus bz square by 2 mu naught is constant. Okay? And if this is constant, so that means that inside the inside this region, we have both P and Bz, right? But outside the pressure is zero. Outside the plasma column, the pressure is zero. So there has to be some external magnetic field, right, which has to balance this, uh, which has to hold this plasma column, right? So which is given by B naught. So you can think of this as P plus Bz square by 2 mu naught is equals to B naught square by 2 mu naught, where B naught square is the magnetic field outside the plasma column. Right. So that was about the pinch instability. Now we are going to move into something called the interchange instability. So what happens here? The concept is that, I'm not going to derive this explicitly, but I'm just going to motivate this result. So what we have over here is that, so the so in initially we have this, uh, you know we have a magnetic field uh, in the direction into the screen, and this will be the y direction, right? And this is the x direction, this is the z direction. So we have the magnetic field in the y direction initially, but what we do is that we replace this plasma from the upper layer, and we just replace it with some of the plasma from the lower layer, which has some magnetic field. So this is the configuration after that interchange has happened. Okay, so now we want to study uh, whether this interchange is stable or unstable, and yeah, what will happen if it's unstable, right? So okay, so let's just see that, so what are the major energy. So we want to calculate the energy of the system initially, and then we want to calculate the energy of the system after the interchange has taken place. And if the energy of the system after the interchange has taken place is lower than the energy of the system initially, that means uh, that then system after the interchange is more stable, right? So it favors the interchange. So that system will become unstable, right? Because there will be more interchanges happening to reduce the energy of the system, and that system will be unstable. And then we'll see how that instability propagates in time or space. Okay. So let's have a look at the energy first. Okay, so interchange instability. So what does the energy, total energy of the system consists of? Right? So if we have to calculate the delta W, so we have to check the change in the internal energy, which is given by this, plus the change in the magnetic energy. So these are volume integrals over the whole volume. Right? Okay. So initially, what we had uh, was this: uh, the magnetic field was balanced by the gravitational force. Okay. So this was initially what we have. Now, after the interchange, what happened is that the total magnetic energy of the system will remain constant because the magnetic field has gone to the upper layer, right? But the total system energy will still remain constant. Right? So, total magnetic energy of the system will remain constant because there is no loss of magnetic field. But what will change is the potential energy of the system since you have plasma from the upper layer brought to the lower layer, right? And the change in that potential energy is given as delta z d3x. Okay. And since the delta z is negative, so this whole term, so this delta w is negative. So that means the energy of the system decreases after the interchange, and which leads to a more stable configuration, and therefore, you know, uh, well, this becomes instable. Okay, so let's see. Okay, now let's talk about answers of that instability. Okay, so let's go back to the slide. So if you look at this image, okay, let me make it full screen. So if you look at this image, right? So what is happening over here is that, well, let's say that, uh, so let's say the magnetic field direction over here is again uh, inside the screen, okay? and 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 therefore, so there will be some currents that are generated due to this perturbation that is over here, right? So what will happen is that since uh, at the top of this wave, so the current is J2, and at the bottom of this wave the current is J1. So what will happen is that since the total plasma that is balanced, total pressure of the plasma that is balanced by this bottom layer is slightly more than the top layer. So the J1 will be greater than J2. So the current at this bottom crest of the wave will be greater than that at the top crest. And if the current is greater, it will give rise to an electric field, and it will give rise to charge separation along these boundaries, right? And similarly, you will have this uh, this E cross B drifts at the bottom layer in the downward direction, right? So because the electric field is in this direction, the magnetic field is in this direction in the top part, whereas uh, in the in this bottom part and in the top layer you have this electric field in this direction, right? because because as I said, since the current is dominated over here, so this will lead to a flow of uh, separation of charges accordingly, right? And yeah, so and similarly the separation of charges in the top layer will be opposite, and similarly the electric field directions will be opposite, and therefore the E cross B drift velocity, um, drift direction, the force due to the Lorentz force direction will be downward in this direction, and in the top rest it will be outward upward. So what it will do is it will make the instability more pronounced, and it will even uh, perturb the layers more. Okay. So similar to this thing is, what if we have some plasma over here initially? So the flux was phi b1 over here, and the flux outside this region is phi b2. So what if we have an interchange of flux between these two regions, right? So what if we replace this phi b1 with phi b2 and phi b2 with phi b1, right? So what will happen then? So let's see that. So so again we will do the similar analysis. So we will see what is the change in uh, energy. So the delta W is given by this thing, right? So we are not considering the internal energy of the fluid, so only the magnetic energy is there. And magnetic flux is B times A, right? So we can actually do like this. So B square A square, and then we have divided by A, right? So this will be this. Now, what we want to see is that what is the change before and after the interchange. Okay, so this is before the energy uh, contained in the B2 region. Okay, sorry, the 2 region, not B2. Phi B is the magnetic flux. So basically, the energy. So this was the B2 region. Right? So this is the yeah. So this is the energy. Wait a minute. Yeah. Sorry. So this is the final energy, because we are uh, we are integrating over the length and the area of the one region. Okay. So this is the final energy minus the initial energy. Okay. And similarly for the final energy and initial energy of the, so this phi B1 flux is now gone into the 2 region, right? So this will be the final energy, and the initial energy was when it was in the 1 region. Okay. And if we just simplify this, this will be something like this: 1 minus A1 by E2 dl2 by dl1 dl1 by dl1. Okay. So this is integration. Now what we are going to do is we are just going to use the continuity equation, and uh, yeah, so this is A1 dl1 equals to A2 dl2, and again calculate this thing, and it turns out this will be something like this. Right. So if we have phi b2 greater than phi b1, so that means the flux outside was higher, and if we, you know, interchange the flux in the inside region, so in that case, for delta W to be negative, dl2 has to be less than dl1, right? Or sorry, I opposite. So dl2 has to be greater than dl1. Okay. So then, this is the condition for instability. Instability condition. Okay. Right. So this is the instability condition. So it just means, so if you look at this figure, the right figure here, so here what it says is that, so you have this kind of a sausage pinch kind of a structure which we studied over here, right? So so this was the mostly the Z pinch, right? So you have B in the phi direction, and if you have higher flux in the B2 region, right, and DL2, which is the length along the magnetic field, is greater than DL1, which you can see from the figure itself the that the circumference of the circle in the L2 region is higher than in the L1 region. So the only condition for this instability is that uh, the flux in the B2 region should be higher than the flux in the B1 region. So in that case, what will happen is that this instability will grow, and as you see that these waves will become more prominent. So this region will keep on shrinking, and this region will keep on expanding. So that is how the sausage pinch instabilities can develop, and these region will keep on shrinking, and you know, unless this magnetic flux tubes get separated. Okay. Okay, so that is how these instabilities work. I guess it's clear. Let me know if you have any questions, because after this we are going to move into a different. So now we move on to turbulence. Okay. So right. So what does turbulent flows mean? So turbulent flows are characterized by random fluctuations, so mean flow. So we are gonna study turbulence with the help of uh, something called the Reynolds decomposition, which is given like this. So any observable of the fluid. So in this case, let's take the velocity, because that's how decomposition is done. So the velocity of the fluid can be decomposed into a mean part and a turbulent part. So the mean velocity is basically, ideally it should be the ensemble average, right? But in this case, we are just going to do a spatial average of the velocity, right? And over that spatial average, we'd study whatever the variation is that we're going to categorize as the turbulent part, which is denoted as E1 prime. Okay. Now, from there, we can define the Reynolds stress tensor as Rij equals to E1 prime Uj prime uh, averaged, right? So bar represents the average. This is the mean velocity definition, of course, and the turbulent kinetic energy is defined like this. And the intensity of turbulence is defined in terms of the kinetic energy and the mean velocity. Okay, so this parameter is a measure of turbulence. Okay, now the question is, how does this turbulence travel in the fluid, right? Or how does this turbulence propagate with time in the fluid? Right? So to study this, uh, Carman and Howard got this equation in terms of this turbulent part of the fluid velocity, which is given as u prime. Okay? And so we are just going to motivate this equation a bit. We're not going to exactly derive this, but maybe if I have time, I may post some post the derivation in the drive. But right now we're just going to motivate the how this equation comes about and what does it mean. So before that, as I said, Rij is ui prime uj prime, but uh, it has a delayed correlation, right? So this is at x and this is at x plus r. Right? So this was for the 1 point statistics where you have uh, correlation at the same point, right? But for 2 point statistics, this is how it looks like. And in the lecture, the professor has given a um, logical explanation of why turbulent cannot be studied with 1 point statistics. So it just simply means that if you just take average of this equation, then the average uh, part of this will come out to be zero. Right? So you need to have um, correlation of uh, UI, UJ kind of terms, right? So which we have over here. Okay. Okay. So let's motivate how this equation comes out to be. So so this actually comes directly from the momentum equation. So this is the Karman-Haworth equation. Right? So Rij, as I said, is Ui xt Uj x plus Rt average. Okay. So Rij is, so in the lecture also, if you see, the professor has written Rij in this form, right? Which is just a simplified form of this. So this he has taken as A, this he has taken as B, right? So we can write anything, f minus g, any function with with this. Okay. So now if you impose the incompressibility condition, which states that duj drj equals to 0 and duj x plus r drj is also equals to 0, right? So what you will get, okay, so what you will get, so if you just multiply this equation with uj, and you can take that uj inside. So what we'll have is d drj of uj times uj x plus r equals to 0. So which is just del rij del rj equals to 0. Okay. So now if you just put the value of rij, this over here in this equation, you can get a relation between g and f, which turns out to be something like this, del f del r. Okay. So this calculation is a little bit tedious, but I will post this derivation in the Google Drive. Okay, so this is how it comes out to be. Now, what we'll do is that, so we are just going to take the momentum equation, which is del t of ui Just give me a minute. Uh, yeah, del. Let's not average it now. So UK del UI del XK or RK minus del P del RI plus nu del square UI. Okay, so this is one equation. Similarly, you can write the same equation at the position uh, x plus r. So the position the all the values at x plus r is determined by prime, like here. So u prime is the value of u at x plus r. Okay. So similarly, we can write the equation like this at some other x plus r distance del square uy prime. Okay. So P prime is the pressure at. So let's write it as R prime. Okay. Yes. Right. So now what we do is we multiply this equation with ui prime and we multiply this equation with uy and we add it up. Okay. So if you do that, again, I will not derive the whole thing, but if you do that and then take an average, so you will get something like this. Uj prime uk del ui del rk plus ui uk prime del uj prime del rk prime. Okay, so you can see that uj prime multiplied with this and uj prime multiplied with this and ui multiplied with this will give you this term, the first term, and this will come from if you multiply uj prime with this, you'll get this, and if you multiply ui with this, you'll get this. Right? And then this will be equals to minus uj prime del p del ri average. So all these are averaged, right? After we average this, you will get this plus nu del square plus del prime square. So this will be del prime. Right? Del prime is just derivative with respect to quantities at r x plus r ui uj prime averaged. Okay, so this is how the equation will reduce down to. Now, so there is one thing which we have done earlier is that if we take this uj prime inside, right? So just like because this term is zero, so we will get a total derivative of pu, right? And if we take the like use the divergence law, this will vanish. Right? So these two terms will vanish. Okay. Now this term survives. Okay, and these two terms again survives. Now these two terms. Okay. So again, I will not exactly derive this, but these two terms can be written in terms of, so like this, u1 x prime is u prime cube, sorry, h rt r1 by r. So this is the definition of h, which is called the triple correlation tensor. Okay, because it depends on the correlation of three terms, three velocities, and this is actually related to this. So right, So what will happen is that, uh, well, I mean, as the derivative of this u's are zero, so we can take this inside. So it will be something of the form del r of this triple product of u's. Right? So at the end, so this term, the first term, will come out to be del t of u prime square. Okay? The second term will be something del r of some triple correlation. So del r of this is triple correlation. Okay. And the last term is some diffusive term, which is nu times uh, nu times del square of del r square of this u. This is again double correlation, right? U prime square. So, well, to understand the physical meaning of each of these terms is that this first term tells you about the rate of change of longitudinal correlation. The second term tells you about nonlinear effects, or how the energy is transferred between different scales, right? And the third term is how the double correlation function diffuses out, right? So this term talks about how the energy is getting cascaded uh, into smaller scales, and this term is how the energy is getting diffused out. Okay, so this is the physical motivation of this Kalman-Haworth equation, and another way to understand turbulent flow is through Reynolds number. So as we have earlier studied, the Reynolds number is the proportion ratio of the advective term v dot del v with the viscous term nu del square v, and this turns out to be of the order of ul by nu. And if the viscosity dominates, so the viscosity uh, dissipates all the uh, turbulence, right? So we'll have a laminar flow, whereas in case of high Reynolds number, where the nonlinear term dominates, which is the advective term, that it will have turbulent flow, right? Right. So this is for turbulence. Now we will just study one prescription of this turbulence, of how to uh, quantify this turbulence, and to study more about the energy cascade, which we also saw in the Kalman-Haworth equation. So Richardson and Kolmogorov has this prescription where they said that, in a turbulent system you have these eddies, or uh, turbulent flow, which can dissipate their energy into smaller and smaller scales, and finally uh, into the smallest scales where we don't have any turbulence. So the scale where we don't have any turbulence is the scale where Reynolds number is equals to 1, because as we said that higher Reynolds number gives rise to higher turbulence. So Reynolds number equals to 1 is the scale where turbulence is 0. Right. So we will just study what Kolmogorov said in his prescription. So let's again. Well, before that, let me just state what we are going to do is that. Um, so so Kolmogorov's proposed his minus 5/3 law, which states that the energy spectrum depends on the um, energy dissipation rate epsilon and the wave number k in this as the power of minus 5/3. Okay, so right, where ck is the Kolmogorov constant. Okay, so this just states that at which wave number would give rise to what energy and so on. Okay, so where does this come from is Okay, let me just go back to my notebook and explain it. Okay, so it actually comes from the Euler's equation, which is or the Navier-Stokes equation actually. So this is the external forcing, right? So F is the external forcing. Now, if we just consider steady state and if we neglect the pressure, so this term goes to zero and this term goes to zero. So if we just neglect these two terms, we're left with these two terms. Okay. So this is the forcing. Okay. And uh, now what will happen is that, so in the lecture it was said that if you have this big eddies, what will happen is that as the system goes on, they will reduce down to smaller and smaller eddies, and finally this turbulence will dissipate, right? So in this intermediate scale, this forcing term is actually balanced by the by this inertial uh, by this advective term, right? But as the scale goes on and this eddies gets dissipated, this forcing term is then balanced by this uh, dissipative term. Okay, so that is what the concept is. But let us see how Kolmogorov get to the 5/3 law. So as I said, turbulence is present when we have Reynolds number much higher. So when we have LV much greater than nu. But when nu starts dominating, the turbulence will dissipate. So this is the dissipative regime. This is, you can call it the inertial regime. This is the turbulent regime. Okay. Okay. So now in the dissipative regime, what will happen is VD, LD. So L is the length of these eddies. Okay. So LD by nu will be equals to 1, because as I said, in the dissipative regime, Reynolds number is equals to 1, because and this is the turbulent regime. Okay. So this just implies LD VD is nu. Now, what is the energy dissipation rate? Epsilon. It just means that energy by time, right? So just from dimensional analysis, and time is given by L by V, which is given like this, right? So, if we consider that the energy dissipation rate is constant throughout as the system goes from turbulent to the dissipative regime, so in that case, VL cube by L is proportional to VD cube by L. Okay. And it is proportional to epsilon. And since epsilon is uh, uh, a constant, as I said, so this VL is proportional to L to the power of 1/3, right? Now, let's see. Okay, so epsilon is proportional to Vd cube by Ld, which is proportional to nu cube by Ld to the power of 4. So we're just using this relation. Ld Vd is proportional to nu, right? So we just replace Vd with nu by Ld. So this is nu cube by Ld cube, and there's one Ld, so Ld to the power 4. So this will give you Ld proportional to nu cube by epsilon whole to the power of 1 by 4. And then we can obtain Vd as nu by Ld, which, and then putting Ld from here, we will get nu epsilon by nu cube 1 to the power 1 by 4. In this case, Vd is epsilon nu 1 to the power of 1 by 4. Okay. Right. So epsilon, as I say, remains constant even in the turbulent regime, even when in the inertial regime, and in the dissipative regime. So this is constant throughout. So therefore, you can get the length scale in this turbulent regime versus the length scale in the dissipative regime, and you can compare like how much has the length decreased from the turbulent to the dissipative regime using this velocity. Okay, and this will turn out to be, so v we can replace from here e nu to the power of 1 by 4, right? Or let's see, so what we'll do is v we can replace with mm, okay, so let's not go here first. So let's see L by LD. So we're just going to replace LD with this, right? And so LD is nu to the power of 3 by 4 by epsilon to the power of 1 by 4. And L we are going to replace with this. So L we are going to replace with V cube by L, V cube by epsilon. And LD we are going to replace with this, nu to the power of 3 by 4 by epsilon to the power of 1 by 4. Right? So this will reduce down to V cube by nu to the power of 3 by 4 L by V cube whole to the power 3 by 4. And this will turn out to be nu L by, sorry, VL by nu whole to the power of 3 by 4. I hope I got this right. So from here you get V cube by nu to the power of 3 by 4. And from here you have epsilon to the power of 3 by 4. Epsilon to the power of minus 3 by 4. And epsilon to the power of minus 3 by 4 is L by V cube whole to the power of 3 by 4, right? Okay, so this will be VL by nu whole to the power of 3 by 4. And if you do L by LD, so this is just the Reynolds number, right? VL by nu. Reynolds number whole to the power 3 by 4. So similarly, V by VD the velocity is given as in terms of Reynolds number. So we can get the length in the turbulent regime to the dissipative regime, what's the change in length, just from knowing the Reynolds number of the flow. Similarly, we can get the velocity in the turbulent and the dissipative regime just from knowing the Reynolds number like this. Okay, so another analysis like the spectrum or the Kolmogorov minus 5/3 law, which I was explaining there. So that can be obtained from, so this wave number KL is proportional to 1 by length. Okay, so half of V square is equals to 0 to infinity EK dk, right? So this is just the energy. The kinetic energy is equals to the energy over all K. So dimensionally, this will be like this. And if you do a dimensional analysis of energy, energy is L cubed to the power of minus 2, right? And if you just, assume that, uh, uh, let's see this as well, right? So, so energy is V square by K, right? So V square has, uh, V square is L, so V is L t to the power of minus 1. So V square is L square t to the power of minus 2 divided by K, and divided by K, and K is 1 by L. So into L, right? So that is L cubed t to the power of minus 2. So we just get the dimension of EK from here. Okay. Now, if we just consider EK to be a function of epsilon and K, which respectively has dimensions of, so epsilon, if you remember, has dimensions of V square by V cube by L, right? So V cube is, V is L to the minus 1, so L cube t to the power of minus 3 by L will be L square t to the power of minus 3, and K is 1 by L, right? So if you just do a dimensional analysis, so EK will turn out to be C times e to the power of 2/3 K to the power of minus 5/3. Okay, so if you can, well, if you can just verify this. So let's just verify this. So epsilon to the power of 2/3 will give you L to the power of 4 by 3 t to the power of minus 2, right? And k to the power of minus 5/3 will give you L to the power 5/3. Yeah. So if you just multiply this, this will be t to the power of minus 2, and this together, L to the power of 9 by 3, which is L cube. So yeah, so this is verified. Okay, so this is how we got the Kolmogorov's 5/3 law. And so if you just plot Ek to the power of, with K, right, energy with respect to K, so it will look something like this, right? So, so this region, the slope will be minus 5/3. Well, if we just plot log actually, okay. So the slope will be minus 5/3, right? And this is the region where this dissipation is taking place. Okay. So okay, so that is pretty much it, and yeah. So this is uh, how the turbulence propagates and the cascade of energy takes place from larger eddies to smaller eddies, right, until the dissipation by viscosity takes place. Right? So, right. So, any questions so far? So, if not, so these are the references for this week. So, mainly, I've followed this book by Garnett and Bhattacharya. This one. So, if you are going through this book, they have it is a good chapter on magnetohydrodynamic waves. So go through that and let me know if you have any other questions. So that is probably, let me see, chapter 6. Chapter 6 is the one where they have talked about all the magnetohydrodynamic waves and the instabilities and all those things. Okay. So I guess that is it for this week. Uh, we'll meet again on next week. Thank you.